What secrets lie hidden in the vast universe? Is there other life in the universe? From the enigmatic depths of black holes to the invisible force of dark matter, the universe is full of questions that challenge our understanding. Join us as we explore these cosmic mysteries and uncover the secrets that lie beyond the stars. Deep within the darkness of a black hole, an abyss challenges our very understanding of physics and reality. When a star collapses under the force of its own gravity, it can create a black hole, a region in space where gravity is so intense that not even light can escape its grasp. At the center of this black hole lies a singularity, a point of infinite density where the laws of physics, as we know them, break down. Space-time itself is contorted beyond recognition, and theories such as general relativity and quantum mechanics collide, producing paradoxes that scientists are still trying to unravel. Approaching the event horizon, the boundary separating the black hole from the rest of the universe, the gravitational pull becomes incredibly powerful, dramatically distorting both space and time. If one could survive the journey, the experience would be mind-bending. Time would appear to slow down, and the universe outside the black hole would seem to speed up, a process known as time dilation. The further you descend, the stronger these effects become until ultimately, all paths lead to the singularity. Here, matter is crushed to infinite density, and space-time becomes infinitely curved. The nature of the singularity remains one of the biggest enigmas in modern cosmology, tantalizing scientists with questions about the true nature of gravity, quantum mechanics, and the fabric of the universe itself. Black holes emerge from the dramatic deaths of massive stars whose lifespans stretch across millions to billions of years. When a star more than 10 times the mass of our Sun exhausts its nuclear fuel, it no longer generates the outward pressure needed to counterbalance the inward pull of gravity. As a result, the star undergoes a massive collapse. This cataclysmic event often culminates in a supernova, an explosion so luminous that it can briefly outshine an entire galaxy. The remnants left behind form the core, compacted into a point of infinite density known as a singularity, enclosed by an event horizon. This boundary delineates the black hole beyond which no information can escape, marking the birth of a stellar-mass black hole. However, not all black holes form from collapsing stars. Supermassive black holes, found at the centers of galaxies, including our Milky Way, present a greater mystery. These behemoths, ranging from millions to billions of times the mass of our Sun, may have grown through the gradual accumulation of matter and the merging of smaller black holes over billions of years. Another theory posits that they formed from massive gas clouds in the early universe, directly collapsing without first becoming stars. Despite the different possible origins, all black holes share the defining characteristic of an event horizon, within which the pull of gravity is so overwhelming that escape becomes impossible. This phenomenon, a gateway to the most extreme conditions in the cosmos, continues to captivate astronomers and physicists striving to understand the universe's most enigmatic entities. Indeed, black holes can merge, an event that not only alters the structure of the universe but also sends ripples through the very fabric of space-time. When two black holes start their cosmic dance, they spiral ever closer due to the emission of gravitational waves. These are ripples in space-time, predicted by Albert Einstein's theory of general relativity over a century ago. As they draw nearer, the black holes accelerate, culminating in a dramatic collision and merger. This cataclysmic fusion results in a single, more massive black hole, and the energy released in this process is so immense that it distorts space-time itself. The final moments of such a merger are nothing short of extraordinary. The gravitational waves produced during the spiraling and merging phases offer a literal shake of a universe. Detectors such as LIGO and Virgo have observed these gravitational waves, confirming both Einstein's predictions and the existence of black hole mergers. When the two black holes coalesce, some of their combined mass is converted into gravitational wave energy, creating a vibration that spreads across the cosmos at the speed of light. The newly formed black hole then settles into a quiescent state, emitting a final series of gravitational waves, known as the ring-down phase. These cosmic collisions not only provide insights into black hole properties, but also serve as powerful confirmations of the dynamic and violent nature of our universe. The event horizon of a black hole is the ultimate boundary in space-time, a point of no return that separates a region where the gravitational pull is unrelenting from the rest of the universe. Imagine it as an invisible shell surrounding the black hole. Once anything, matter, or light passes its threshold, it is irretrievably drawn inward. The term event horizon aptly describes this limit, as any event occurring beyond it is forever hidden from outside observers. This concept stems from Einstein's general theory of relativity, which describes how massive objects warp the space-time around them. Once an object crosses the event horizon, escape becomes impossible because it would require traveling faster than the speed of light, which is a universal speed limit according to our current understanding of physics. Photons, the particles of light, are the fastest entities in the known universe, yet even they cannot break free from the black hole's gravitational tug once inside the event horizon. This results in the black hole appearing completely black against the backdrop of space, hence the name. Despite this, the vicinity just outside the event horizon can be extraordinarily dynamic, often marked by high-energy phenomena as matter accelerates and heats up before being swallowed. Thus, while the event horizon acts as a one-way gateway into a realm of mystery, it also marks a boundary where our understanding of the universe's most extreme conditions begins. Black holes, seemingly eternal voids in the cosmos, can indeed lose mass and even evaporate over time through a process known as Hawking radiation. This groundbreaking concept, proposed by physicist Stephen Hawking in 1974, merges principles from quantum mechanics and general relativity, fundamentally altering our understanding of black holes. Near the event horizon, the intense gravitational field causes quantum fluctuations, leading to the spontaneous creation of particle-antiparticle pairs. Normally, these pairs annihilate each other almost instantly, but near a black hole, one particle can fall into the black hole while the other escapes into space. This escaping particle effectively reduces the black hole's mass, a process that, over incredibly long timescales, can cause a black hole to lose energy and shrink. Imagine it as a black hole gradually radiating away its blackness, a phenomenon that seems to contradict the idea of black holes being perfect cosmic traps. Singularities are the enigmatic heart of black holes, where the known laws of physics break down in the face of infinite density and zero volume. At the core of a black hole, the gravitational pull becomes so intense that it causes space and time to collapse inward, compressing matter to a point of infinite density, known as the singularity. This is where our current understanding of the universe hits a wall. Conventional descriptions of space-time, as outlined by Einstein's general relativity, simply cannot handle the conditions present at a singularity. In this bizarre region, gravitational forces are so extreme that they warp space-time to an infinite degree, leading to a point where both the curvature of space and the gravitational field become infinite. This makes a singularity a region with no size, and paradoxically, a place where everything is crushed into an infinitely small space. Theories from quantum mechanics, which govern the smallest scales of the universe, have not yet been reconciled with general relativity to describe what truly happens at these singularities. This discrepancy is a major driver for physicists seeking a unified theory of quantum gravity, a model that would seamlessly integrate the laws governing the very large and the very small. Despite the theoretical conundrums, singularities continue to intrigue scientists and serve as a powerful reminder of the limits of our current knowledge. They press the boundary where our understanding transitions from the known into the realm of speculation and uncharted physics. While the exact nature of singularities remains one of the biggest mysteries in astrophysics, these enigmatic points are crucial to unlocking deeper truths about gravity, space-time, and the very fabric of the cosmos. Black holes, often perceived as cosmic drainers, exert an influence on the universe that extends far beyond their immediate vicinities. These gravitational titans impact the structure and evolution of galaxies, drive cosmic processes, and even play a role in the distribution of matter in the universe. At the centers of most galaxies, including our Milky Way, lie supermassive black holes with masses millions to billions of times that of our Sun. These colossal entities don't merely sit passively. They sculpt around them through their immense gravitational pull and energetic activities. When a black hole consumes matter, it often does so in a dramatic fashion, with infalling material forming an accretion disk around it. This process can unleash powerful jets of particles that shoot out for thousands of light years, influencing star formation in the surrounding galaxy. The energetic outflows, called active galactic nuclei, can regulate the rate at which new stars are born by heating up the interstellar medium or blowing it away entirely. This feedback mechanism helps explain why there is a correlation between the size of a galaxy's central bulge and the mass of its central black hole, a relationship known as the M-sigma relation. Furthermore, Black holes play a crucial role in the cosmic web's underlying structure, the large-scale network of galaxy clusters and voids. During galaxy mergers, the black holes and the merging galaxies can also collide, profoundly affecting their environments by releasing gravitational waves. These interactions can drive the evolution of galaxy clusters and contribute to the overall dynamics of the universe. As such, although black holes might seem like isolated and destructive entities, they are integral to the cosmic symphony, orchestrating the formation, evolution, and ultimate fate of the vast structures that populate our universe. Dark matter is one of the universe's most profound and elusive mysteries. Unlike the ordinary matter that makes up stars, planets, and everything we see around us, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Its presence was first inferred in the early 20th century when astronomers noticed discrepancies in the motion of galaxies that couldn't be explained by visible matter alone. The story of dark matter's discovery began with Fritz Zwicky in the 1930s. Zwicky observed the Coma cluster of galaxies and calculated their total mass based on their luminosity. Surprisingly, he found that there was far too little visible matter to account for the galaxies' observed velocities. They were moving too quickly to be held together by only the mass of the stars and gas visible to telescopes. Zwicky coined the term dark matter to describe this unseen mass. Further compelling evidence came from Vera Rubin in the 1970s when she studied the rotation curves of spiral galaxies. Rubin observed that stars in the outer regions of galaxies rotated at similar or higher speeds compared to those near the center. According to Newtonian physics and the distribution of visible matter, the outer stars should have been moving much slower. The consistently high rotational velocities implied that there was additional unseen mass distributed throughout the galaxies, exerting gravitational influence. Today, dark matter is thought to make up about 27% of the universe's total mass energy content, far surpassing the roughly 5% of ordinary matter. Its elusive nature has propelled scientists into devising various theoretical models and conducting sophisticated experiments to detect it indirectly, but its true identity remains one of the greatest enigmas in modern cosmology. Whether it comprises exotic particles, black holes, or something we haven't yet conceptualized, dark matter holds a key to understanding the universe's full composition and its ultimate fate. Dark energy is an even more mysterious component of the cosmos than dark matter, playing a crucial role in the accelerating expansion of the universe. While dark matter pulls things together with its gravitational effects, dark energy pushes the universe apart. It is an unknown form of energy that permeates all of space and contributes approximately at least 68% of the universe's total mass energy content, dwarfing both ordinary matter and dark matter. The existence of dark energy was inferred from observations of distant Type Ia supernovae in the late 1990s. These supernovae, which serve as cosmic standard candles due to their consistent luminosity, were used to measure cosmic distances and the rate of the universe's expansion. Scientists, including Sol Perlmutter, Brian Schmidt, and Adam Rees, found something unexpected. These supernovae were dimmer than predicted, indicating that the universe's expansion was not slowing down as previously thought, but accelerating. This surprising discovery led to the conclusion that a mysterious repulsive force, dubbed dark energy, was driving this accelerated expansion. The nature of dark energy remains one of the biggest questions in cosmology. One leading hypothesis is that it is related to the cosmological constant, lambda, introduced by Albert Einstein in his equations of general relativity. The cosmological constant represents a constant energy density filling space homogeneously. Another hypothesis posits that dark energy is a dynamic field called quintessence, whose properties evolve over time. Regardless of its exact nature, dark energy's influence on the universe is profound. It stretches space itself, accelerating the rate at which galaxies move away from each other, leading to a future where distant galaxies may drift so far apart that they become invisible to us. This expansive force not only shapes the large-scale structure of the universe, but also influences its ultimate fate, potentially driving it towards a cold, isolated end in what is often referred to as a big freeze. By uncovering the secrets of dark energy, scientists hope to unlock deeper insights into the fundamental workings of the universe and its destiny. The nature of dark matter remains one of the most captivating, unresolved questions in cosmology and particle physics. Given its substantial contribution to the universe's total mass energy content, understanding dark matter is crucial for grasping the large-scale structure and evolution of the cosmos. Several leading theories propose different candidates for dark matter, each with its own set of characteristics and implications. One of the most favored theories posits that dark matter consists of weakly interacting massive particles, WIMPs. These hypothetical particles interact only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. WIMPs are compelling candidates because their properties neatly fit within the framework of the standard model of particle physics, particularly extensions like supersymmetry. Despite extensive efforts, including experiments in deep underground detectors such as a large underground xenon LUX experiment, direct evidence for WIMPs remains elusive. Another prominent theory suggests that dark matter could be composed of actions, ultralight particles that were originally proposed to solve problems in quantum chromodynamics, the theory that describes a strong nuclear force. Actions interact even more weakly than WIMPs and can be detected indirectly by observing their conversion into photons in the presence of strong magnetic fields. Experiments like the Action Dark Matter Experiment, ADMX, are in pursuit of these elusive particles. A third intriguing possibility is that dark matter consists of primordial black holes, small black holes formed in the early universe shortly after the Big Bang. Unlike the supermassive black holes that reside at galactic centers, these primordial black holes will be spread throughout the universe and could make up a significant portion of dark matter. Studies of gravitational lensing and the cosmic microwave background help constrain this possibility, though it has not been definitively proven. By employing these varied and complementary methods, scientists have built a robust case for the existence of dark matter and gained a clearer picture of its distribution and influence. Whether through rotation curves of galaxies, gravitational lensing, analyses of the cosmic microwave background, or galaxy cluster dynamics, the effects of dark matter are measurable even if the substance itself remains unseen. If dark matter particles annihilate each other, they could produce gamma rays, neutrinos, or other standard particles. Observatories like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer AMS-02 on board the International Space Station search for such signals. For example, an excess of gamma rays detected from the center of the Milky Way has been speculated by some researchers to be a potential sign of dark matter annihilation, although the source of these rays remains under debate. Collider experiments, such as those conducted at the Large Hadron Collider LHC at CERN, also contribute to the search for dark matter. By smashing protons together at incredibly high energies, physicists hope to create dark matter particles directly, which would be inferred from missing energy and momentum in the aftermath of the collisions. If dark matter particles interact with regular matter through the weak nuclear force or other forces predicted by theories like supersymmetry, they could leave identifiable signatures in the data collected by detectors like ATLAS and CMS. Despite these multifaceted efforts, no conclusive evidence of dark matter interacting with regular matter has been found to date. The persistence of these null results confines the strength of potential interactions to be exceedingly weak, if they exist at all. However, the lack of detection also helps refine theoretical models and steers subsequent experimental designs. Ultimately, while dark matter primarily reveals itself through gravitational effects, the tantalizing question of its interaction with regular matter remains a driving force behind many of the most advanced and sensitive experiments in modern physics. Unraveling this mystery could herald a new era in our understanding of the universe's fundamental components and forces. Deep beneath the Earth's surface, in the quiet depths of old mines and dedicated underground laboratories, extraordinary experiments are underway to unravel one of the cosmos's greatest mysteries, dark matter. Scientists have embarked on a quest, using sophisticated detectors to catch the elusive particles that comprise this invisible yet seemingly omnipresent substance, which is believed to constitute about 85% of the universe's mass. One groundbreaking experiment is a large underground xenon LUX experiment, buried almost 1 mile underneath the Black Hills of South Dakota. This detector uses a liquid xenon target to watch for rare interactions with dark matter particles. When a dark matter particle collides with a xenon atom, it is expected to produce a faint flash of light, detectable by the sensitive photosensors encapsulating the xenon. Another fascinating project is the Cryogenic Dark Matter Search, CDMS, located deep in the Soudan mine in Minnesota. This experiment employs ultra-cold germanium and silicon crystals to identify dark matter particles through their collisions with the atomic nuclei within these crystals. When a dark matter particle hits a nucleus, it produces tiny vibrations and ionization, both of which are meticulously recorded by a detector. To minimize interference from cosmic rays and other background noise, these experiments are located far below Earth's surface, providing a shield that helps ensure that any detected events are genuinely from dark matter interactions. These cutting-edge experiments illustrate the lengths to which scientists will go to peel back the veil on this cosmic enigma, combining human ingenuity with a rugged, silent guardianship of the Earth itself. Dark energy stands as an enigmatic force that defies our conventional comprehension of physics. It's a mysterious form of energy that comprises roughly 70% of the universe's total energy content and is responsible for the accelerated expansion of the cosmos. According to Einstein's theory of general relativity, gravity should be slowing down the expansion of the universe, but observations, notably from the Supernova Cosmology Project and the HiZ Supernova Search Team in the latter part of the 1990s, revealed the exact opposite. Instead of decelerating, the universe's expansion is speeding up, a discovery that has fundamentally challenged our understanding of gravity and cosmology. This perplexing force seems to operate against gravity, pushing galaxies apart at an ever-increasing rate. The exact nature of dark energy remains one of the biggest open questions in physics. Some theories propose it might be the cosmological constant, an energy density inherent to the fabric of space itself. Others suggest it could be a field similar to the Higgs field, but with different properties, permeating all of space. This accelerating expansion also has profound implications for the ultimate fate of the universe. If dark energy maintains its current effect, it might lead to scenarios where galaxies move so far apart that communication and travel between them become impossible, a chilling concept known as the Big Freeze. Dark energy forces physicists to rethink fundamental theories and hunt for new physics beyond our current standard model, driving a revolutionary shift in our quest to understand the cosmos. The conjecture that dark matter and dark energy could be interconnected is a tantalizing idea that continues to ignite the curiosity and imagination of cosmologists. Both components make up the vast majority of the universe's content, dark matter around 27% and dark energy about 70%. Yet they remain mysterious and elusive. Some physicists propose that these two dark phenomena might not be entirely separate entities, but could instead be two aspects of a deeper, underlying framework yet to be discovered. One intriguing hypothesis is the concept of quintessence, a dynamic field that could potentially unify the roles of dark energy and dark matter. Unlike the cosmological constant, which is a fixed energy density, quintessence would vary over space and time, possibly providing a common foundation for these dark components. Further stretching the boundaries of theoretical physics are models involving extra dimensions beyond our familiar three-dimensional space and time. In some theories, such as those derived from string theory, the interactions within these additional dimensions might manifest in our observable universe as dark matter or dark energy. Others have proposed the intriguing idea of dark fluid, a single substance that behaves like dark matter in some conditions and dark energy in others, governed by a state-dependent equation of state. Observational data from advanced telescopes, deep space probes, and ground-based experiments will be crucial in either supporting or refuting these groundbreaking theories. The potential link between dark matter and dark energy could herald a paradigm shift, reshaping our understanding of the universe and the fundamental forces that govern it. The presence of dark energy has profound and far-reaching implications for the ultimate fate of the universe, introducing scenarios that range from the gradual to the dramatic. One of the most widely discussed outcomes is the Big Freeze, or heat death. In this scenario, dark energy continues to drive the accelerated expansion of the universe, causing galaxies to recede from each other at increasingly rapid speeds. Over trillions of years, stars will exhaust their nuclear fuel and cease to shine, galaxies will disperse, and the universe will become a dark, cold, and sparse place. In this endlessly expanding cosmos, temperatures will approach absolute zero, and the universe will reach a state of maximum entropy, when no thermodynamic free energy remains to sustain processes that increase entropy. Another possibility is the Big Rip. In this more apocalyptic scenario, the influence of dark energy intensifies over time. As it becomes more dominant, it could eventually overpower all other forces, including gravitational, electromagnetic, and even nuclear forces. This escalating effect will begin by tearing apart galaxy clusters, individual galaxies, and eventually solar systems. In the final moments, as dark energy's influence grows exponentially, even atoms and subatomic particles will be ripped apart. The universe would meet a cataclysmic end, disintegrating into a singularity where conventional physics can no longer describe the conditions. A less severe but still transformative possibility is a big crunch. If future observations reveal that dark energy might reverse its effects or diminish over time, the accelerated expansion could slow down, halt, and eventually reverse, leading to a gravitational collapse where the universe contracts back into a high-density state, potentially reinitiating a cycle of expansion and contraction. Each of these scenarios underscores how dark energy fundamentally alters our understanding of cosmic destiny, presenting a range of extraordinary possibilities for how the drama of the cosmos might ultimately conclude. The mystery of what, if anything, existed before the Big Bang remains an open and profoundly intriguing question that continues to inspire scientific inquiry and philosophical contemplation. Following the cataclysmic event of the Big Bang, the universe transitioned through a series of remarkable epochs that laid the groundwork for formation of the first stars and galaxies. Initially, the universe was an incredibly hot and dense plasma of particles, protons, neutrons, electrons, and photons, without any stable atomic structures. This period, known as the Cosmic Dark Ages, lasted for several hundred million years. As the universe expanded, it cooled down, allowing protons and electrons to combine and form neutral hydrogen atoms, a process called recombination. This event decoupled light from matter, leading to the release of the cosmic microwave background, CMB, radiation, a faint glow that still pervades the universe today. With the formation of neutral atoms, the universe became transparent, allowing gravity to begin its gradual work of pulling matter together. Tiny fluctuations in the density of matter, imprinted during the inflationary epoch shortly after the Big Bang, began to grow under the influence of gravity. Regions with slightly higher densities attracted more matter, creating the seeds for the formation of structures. Over time, these overdense regions collapsed to form the first clumps of matter. Within these clumps, gas, primarily hydrogen and helium, began to fall into gravitational potential wells, leading to the formation of dense, cold clouds. Inside these clouds, the gas cooled and condensed, triggering the process of star formation. The first stars, known as population 3 stars, were likely massive and short-lived. They were composed almost entirely of hydrogen and helium, as the heavier elements, metals, had not yet been forged. These massive stars burned their nuclear fuel rapidly, ending their lives in spectacular supernova explosions. These explosions enriched the surrounding gas with heavier elements, setting the stage for the formation of subsequent generations of stars and the eventual complex chemistry necessary for planet formation and life. As these early stars congregated, they began to form the first protogalaxies. The gravitational attraction between these stars and dark matter, which constituted a significant portion of the mass in the universe, facilitated the assembly of larger structures. Small protogalaxies merge over time to build more massive galaxies, a process known as hierarchical clustering. This framework of structures evolved into the galactic and intergalactic networks we observe today. Modern telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, are crucial in unveiling the mysteries of this epoch. They provide snapshots of young galaxies and early star formations, allowing astronomers to piece together this cosmic history. By studying distant, ancient galaxies, scientists can observe the universe as it was billions of years ago, enabling them to explore these formative stages directly. The formation of the first stars and galaxies marks a significant chapter in cosmic history, transforming a homogeneous sea of gas into a universe replete with complex structures, leading ultimately to environments where life could potentially arise. These early processes set the stage for the rich tapestry of astronomical phenomena that we continue to study and explore today. The cosmic microwave background, CMB, radiation is one of the most profound and enlightening discoveries in cosmology, acting as a relic from the early universe. Detected in 1965 by Arno Penzias and Robert Wilson, the CMB is the faint glow of radiation that permeates the entire universe, a remnant from about 380,000 years after the Big Bang. This was a time when the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms, a process known as recombination, allowing photons to travel freely for the first time. These ancient photons have stretched into the microwave part of the electromagnetic spectrum due to the expansion of the universe, creating a uniform background radiation detectable in every direction. Far from being just a faint afterglow, the CMB holds a wealth of information about the early universe's structure and composition. Tiny variations in the temperature of the CMB, known as anisotropies, encode crucial data about the density fluctuations in the early universe, which eventually led to the formation of galaxies and large-scale cosmic structures. Detailed maps of these anisotropies, such as those produced by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have provided insights into fundamental cosmological parameters. These include the age of the universe, its composition, and the rate of its expansion, known as the Hubble constant. Moreover, the CMB offers strong evidence for the theory of inflation, a rapid expansion of the universe immediately following the Big Bang. The tiny quantum fluctuations that existed during inflation were magnified to macroscopic scales and eventually seeded the formation of galaxies and large-scale structures. The CMB's uniformity on large scales, along with its slight anisotropies on smaller scales, supports this inflationary model, constraining the physics of the early universe with high precision. Polarization patterns in the CMB also provide significant clues. These patterns can be divided into E modes, which have been measured with high accuracy, and B modes, which are more elusive and could offer evidence of primordial gravitational waves, ripples in space-time generated during the inflationary epoch. Detecting these B-mode patterns would not only confirm inflation, but also offer insights into the energy scales of fundamental physics, potentially linking cosmology with high-energy particle physics. In addition to cosmological insights, the CMB helps test a standard model of cosmology, known as a lambda-cold dark matter (CDM) model. By comparing predictions from the CDM model with CMB observations, scientists can verify the consistency of our understanding of dark matter, dark energy, and the overall geometry of the universe. Any deviations could point to new physics beyond our current theories, setting a path for future discoveries. The CMB, therefore, is like a cosmic blueprint, offering a glimpse back to the infant universe and answering some of the deepest questions about its origin, structure, and fate. Researchers continue to study this primordial radiation, extracting increasingly refined data and thereby unraveling the universe's early secrets with each new observation. Inflation theory is a compelling hypothesis that aims to fill in crucial gaps in our understanding of the universe's infancy, proposing that the universe underwent an extraordinarily rapid expansion during the very first moments after the Big Bang. Introduced in the early 1980s by physicist Alan Guth and subsequently refined by others, inflation posits that in a fraction of a second, from approximately 10 cubed to 10 cubed squared seconds after the Big Bang, the universe expanded exponentially, increasing in size by a factor of at least 10 cubed. This marked an expansion at a rate far exceeding the speed of light, driven by a high-energy field known as the inflaton field. Inflation theory addresses several perplexing issues that were not explained convincingly by the original Big Bang theory alone. One of the primary problems it solves is the horizon problem. Observations of the CMB radiation reveal that regions of the universe separated by vast distances have very similar temperatures and properties, suggesting they were once in thermal equilibrium. However, without inflation, these regions would have been causally disconnected since the time of the Big Bang, making their uniformity inexplicable. Inflation solves this by proposing that these regions were indeed in close contact before the rapid expansion, thus allowing for the even distribution of energy and temperature. Another significant puzzle inflation addresses is the flatness problem. The observable universe appears to be remarkably flat on large scales, meaning the geometry of space is close to Euclidean. These interactions can lead to phenomena like rapid star formation surges, galactic mergers, and even the ejection of stars from the galactic center at extraordinary speeds. As we delve deeper into the universe's mysteries, the intricate dance between supermassive black holes and their host galaxies continues to reveal itself as a cornerstone in our understanding of cosmic evolution. Cosmic voids are vast, empty regions in the universe that are almost completely devoid of matter, including galaxies, stars, and gas. These immense voids can span tens to hundreds of millions of light years across, making them some of the largest structures in the cosmos. In contrast to the densely packed clusters and superclusters of galaxies, cosmic voids are like the dark, quiet spaces between bustling cities. The formation of these voids can be traced back to the early moments after Big Bang, during the epoch of cosmic inflation. In this period, tiny quantum fluctuations in the density of the primordial universe were rapidly expanded, seeding the initial uneven distribution of matter. As the universe evolved, regions with slightly higher densities began to gravitationally attract more matter, growing into the galaxies and clusters we see today. Conversely, areas with slightly lower densities were left with progressively less matter as material gravitated toward the denser regions. Over billions of years, this gravitational tug-of-war sculpted the universe into a cosmic web of dense filaments and clusters interspersed with vast, empty voids. Cosmic voids offer unique opportunities for astronomers studying dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are relatively empty and less cluttered by luminous matter, they provide clearer insights into the large-scale structure of the cosmos and the underlying gravitational framework. By mapping and analyzing these colossal empty spaces, scientists continue to unravel the story of the universe's formation and evolution, offering glimpses into the mysterious forces that shape our cosmic landscape. Galaxies interact and merge in a grand cosmic ballet dictated by the inexorable pull of gravity. When two galaxies approach each other, their mutual gravitational attraction can set them on a slow, centuries-long collision course. Initially, this interaction manifests as tidal forces, which distort and stretch the galaxies, creating dramatic tidal tales of stars and gas that can extend for thousands of light years. As the galaxies draw closer, their interstellar gas clouds begin to collide and compress, often leading to bursts of intense star formation, known as starbursts. These periods of prolific star creation can light up the galaxies, transforming them into dazzling stellar nurseries. As the merger progresses, the galaxy's central supermassive black holes may also converge, potentially merging to form an even more massive black hole. The final stages of galactic merger are incredibly chaotic, with stars being flung into new orbits and the shapes of the galaxies becoming increasingly distorted until they eventually coalesce into a single new galaxy. This newly formed galaxy typically has a different morphology, often ending up as a more massive elliptical galaxy rather than retaining the spiral structures that might have been present before the merge. The consequences of such mergers are far-reaching. For one, the energetic processes during the merger can trigger significant changes in the galactic environment, such as the activation of quasar-like phenomena if the central black holes accrete material rapidly. Additionally, the mixing of different stellar populations and gas can lead to a more homogeneous galaxy in terms of its chemical composition and age distribution. Furthermore, galactic mergers play a crucial role in driving the overall evolution of the universe, building up the complex hierarchy of cosmic structures we observe today. They are not just spectacular events. They are fundamental processes that forge the galaxies and galaxy clusters that comprise the large-scale structure of the universe. Planetary systems face an uncertain yet fascinating journey when their host galaxies merge. The vastness of space plays a critical role in this process, as stars and their planetary systems are incredibly far apart relative to their sizes. When galaxies collide, the chances of direct impact between individual stars or planetary systems are minuscule. This means most planetary systems survive the merger relatively unscathed, continuing their orbits around their home stars or galaxies' larger structures, like gas clouds, star clusters, and dark matter halos, undergo significant turbulence and reorganization. However, the gravitational interactions during a galactic merger can cause substantial shifts in the orbits of stars within the merging galaxies. These gravitational perturbations can lead to the ejection of some stars from their original positions, sometimes flinging entire star systems into the outer regions of the new merged galaxy or even into the vast emptiness of intergalactic space. For planetary systems that remain bound to their parent stars, these shifts can alter their paths around the galactic center, potentially moving them into different environments with varying radiation levels, densities of interstellar medium, and tidal forces. Moreover, the increased star formation triggered by the merger can lead to nearby supernovae, which may have profound effects on planetary systems. Intense radiation and shock waves from supernovae could strip planetary atmospheres or disrupt orbital stability, especially for planets orbiting closer to their stars. Despite these potential hazards, the overall number of planetary systems affected directly remains relatively low, given the sheer scale and number of stars involved. Thus, while galaxy mergers are truly transformative on a cosmic scale, the microcosm of individual planetary systems tends to endure, riding the waves of these vast interstellar events. The alignment of galaxies over vast distances is a surprising and intriguing phenomenon that hints at the interconnected nature of the universe's large-scale structure. Galaxies are not randomly scattered, but instead appear to be aligned along large filamentary structures in a pattern known as the cosmic web. This web is composed of immense filaments of dark matter and gas, stretching across hundreds of millions of light-years and connecting clusters and superclusters of galaxies. The underlying cause of these alignments can be traced back to the initial conditions of the universe and the influence of dark matter. In the early universe, small fluctuations in the density of matter created slight overdensities and underdensities after the Big Bang. Gravity caused the overdense regions to attract more matter, gradually growing into the large-scale structures we see today. Dark matter, which makes up about 85% of the universe's total mass, plays a crucial role in this process. It does not interact with light, but exerts a gravitational force that influences the distribution and movement of galaxies. As dark matter forms these elongated filaments and nodes, galaxies forming within these structures naturally align along the filaments due to the gravitational pull and the flow of matter. Furthermore, the rotational axes of galaxies can become aligned with these filaments as a result of angular momentum conservation during their formation within the cosmic web. This alignment phenomenon extends over vast distances, with studies showing correlations in the orientation of galaxies separated by hundreds of millions of light-years. These cosmic alignments provide a window into the underlying dark matter framework of the universe and offer valuable insights into the initial conditions that have shaped the large-scale structure since the early moments after Big Bang. As we continue to study comets and their organic compositions, each new finding brings us one step closer to unraveling the grand question of how life began and whether we are alone in the universe. The next wave of space exploration missions promises to push the boundaries of our knowledge and unveil new aspects of our universe, targeting a range of intriguing objectives. One of the most anticipated missions is NASA's Artemis program, which aims to return humans to the moon by the mid-2020s, establishing a sustainable presence on the lunar surface. This mission is not just about revisiting our celestial neighbor, but also about setting the stage for future crewed missions to Mars. Artemis will enable scientists to study the moon's resources in greater detail, particularly water ice at the lunar poles, which could be vital for sustaining long-term human exploration and developing in-situ resource utilization technologies. Meanwhile, enhancing our understanding of Mars continues to be a priority, with NASA's Perseverance rover already exploring the Martian surface, collecting samples that will be returned to Earth by the Mars Sample Return mission in the early 2030s. These samples are expected to provide unprecedented insights into the planet's geology and potential past habitability. Additionally, ESA and Roscosmos are collaborating on the ExoMars program, which includes a Rosalind Franklin rover designed to drill below the Martian surface in search of biosignatures. In the realm of outer solar system exploration, NASA's Europa Clipper mission, slated for the 2020s, will conduct detailed reconnaissance of Jupiter's moon Europa, investigating its subsurface ocean and its potential for supporting life. Another exciting mission is the James Webb Space Telescope, JWST, which has already begun its journey to explore distant exoplanets, the early universe, and the formation of stars and galaxies with unprecedented clarity. JWST will look for atmospheres around exoplanets, potentially identifying planets with conditions suitable for life. Finally, the field of planetary defense is also witnessing advancements with NASA's DART mission, Double Asteroid Redirection Test, a kinetic impactor technique to test our capability to deflect a potentially hazardous asteroid. Collectively, these missions herald a new era of exploration, bringing us closer to answering fundamental questions about our place in the universe, the potential for life elsewhere, and the continued survival of humanity. Space telescopes serve as our windows to the universe, providing clear, unimpeded views of celestial phenomena that ground-based observatories can't achieve due to Earth's atmospheric interference. This unhindered perspective has fundamentally transformed our understanding of the cosmos across diverse wavelengths, from visible light to infrared and beyond. The Hubble Space Telescope, orbiting above our planet since 1990, has become iconic for its stunning imagery and rich scientific contributions. Hubble has allowed astronomers to measure the rate of cosmic expansion with unprecedented precision, lending support to the theory of dark energy, a mysterious force accelerating the expansion of the universe. Additionally, it has captured detailed images of distant galaxies, star-forming regions, and exoplanets, significantly advancing our knowledge about the structure and evolution of the cosmos. Beyond optical observations, space telescopes like the Chandra X-ray Observatory and the Spitzer Space Telescope have delved into the high-energy and infrared realms, respectively, providing insights into phenomena inaccessible to visible light instruments. Chandra's X-ray observations have unveiled the violent behaviors of black holes, neutron stars, and supernova remnants, revealing the extreme conditions that shape these exotic objects. Meanwhile, Spitzer's infrared capabilities enable the study of the early universe, star birth, and planetary formation processes cloaked in dust that blocks visible light. With the recent launch of the James Webb Space Telescope JWST, astronomers are poised to delve even deeper. JWST is designed to peer back in time to the first galaxies formed after the Big Bang and to meticulously study the atmospheric compositions of exoplanets, potentially identifying biosignatures. Each of these instruments expands the frontiers of our understanding, providing piecemeal insights that together weave a comprehensive tapestry of the universe, its origins, and its inexorable evolution. Human space travel beyond the moon presents a tapestry of formidable challenges, both technical and physiological, each demanding innovative solutions. One of the most daunting obstacles is the extended duration of missions to destinations like Mars, which could take 6 to 9 months one way, followed by an extended stay to align with optimal return windows. This duration significantly increases exposure to space radiation, including galactic cosmic rays and solar particle events. Unlike the relatively short journeys to the moon, astronauts on Mars missions would not benefit from Earth's protective magnetosphere, making advanced radiation shielding and potential pharmaceutical countermeasures a critical area of research. Another major challenge is the psychological and physical toll of prolonged weightlessness. Extended periods in microgravity can lead to muscle atrophy, bone density loss, and fluid redistribution, which affects vision and other bodily functions. While the International Space Station, ISS, has provided valuable data on mitigating these effects through exercise regimens and medical monitoring, the time frame for Mars missions will test these countermeasures to their limits. Additionally, the psychological impact of isolation and confinement in a spacecraft for months on end, compounded by the communication delays with Earth that can stretch up to 20 minutes one way, require robust mental health support systems and well-designed habitats that offer some degree of privacy and comfort. Logistics and life support systems also pose considerable hurdles. The need for sustainable life support systems that can recycle water and waste efficiently for extended periods is paramount. These systems must be extraordinarily reliable, with redundancies built in to mitigate failures far from home. Moreover, carrying enough food and supplies for long-duration missions or developing technologies such as hydroponics or bioregenerative life support systems to produce fresh food in space are critical areas of development. Finally, propulsion and energy are significant challenges. Current rocket technology, while advanced, still requires months to traverse the distance to Mars. Nuclear thermal propulsion or advanced ion propulsion systems are among the options being explored to reduce travel time and improve mission feasibility. Human space travel beyond the moon will require a confluence of technological ingenuity, rigorous testing, and international cooperation to surmount these challenges and realize the dream of interplanetary exploration. As humanity prepares to venture deep into the cosmos, a suite of innovative technologies is being developed to meet the unique demands of deep space exploration. One of the forefronts of this advancement is propulsion technology. Traditional chemical propulsion, while vital, is not efficient enough for long-duration missions to destinations like Mars and beyond. Researchers are thus investing in nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP. NTP involves heating propellants such as hydrogen with a nuclear reactor, providing a higher thrust-to-weight ratio than conventional systems. NEP, on the other hand, utilizes nuclear energy to produce electricity that powers ion thrusters, offering high efficiency and extended operational capabilities that can significantly reduce travel time. Future space missions are poised to revolutionize our understanding of the cosmos by addressing some of the most profound questions about the universe's origins, structure, and potential for life. These missions can provide critical insight into the conditions that could support life. This observational puzzle led to the theorization of a mysterious force termed dark energy, which now constitutes about 70% of the universe's total energy density. Dark energy acts as a repulsive force, counteracting the gravitational pull of matter, and thereby driving the accelerated expansion. The exact nature of dark energy remains one of the biggest mysteries in cosmology. It seemingly behaves like a cosmological constant, a term Einstein once introduced and later discarded, representing a uniform energy inherent to the fabric of space itself. However, some theories suggest that dark energy could be a dynamic field evolving over time. Quantum mechanics and general relativity, the pillars of modern physics, struggle to coherently explain this force within a single framework. Researchers are probing deeper with advanced telescopes and instruments, hoping to unlock the secrets of this enigmatic energy. The accelerating expansion hints at a universe heading toward a cold, diffuse future, a profound shift in our understanding of cosmic destiny. To grasp the influence of black holes on the universe's structure, picture these enigmatic entities as cosmic sculptors, shaping their surroundings through gravitational mastery. Black holes, despite their name, are anything but empty voids. Formed from the remnants of massive stars, they possess gravitational fields so intense that not even light can escape. At the centers of most galaxies, including our own Milky Way, lie supermassive black holes with masses equivalent to millions or even billions of suns. These galactic giants exert profound effects on their host galaxies, anchoring them gravitationally and regulating star formation through their powerful accretion processes and jet outflows. When matter spirals into a black hole's accretion disk, it heats up and emits intense radiation, triggering energetic phenomena that can influence entire galaxies. These high-energy jets can expel vast amounts of gas into intergalactic space, affecting the rate at which new stars are born. Imagine these jets as cosmic gardeners, pruning and shaping the galactic landscape. Moreover, black hole mergers, detectable through gravitational waves, contribute to the dynamic evolution of galaxies, sometimes causing dramatic rearrangement of stars and altering cosmic structures. The dance of black holes and their gravitational machinations thus plays a critical role in the grand architecture of the universe, sculpting everything from the distribution of galaxies to the intricate web of the cosmic fabric itself. Magnetic fields play a crucial yet intricate role in the life cycle of stars, acting like invisible threads weaving through the tapestry of star formation. In the cold, dense regions of molecular clouds, where stars are born, magnetic field exerts significant influence over the gas and dust collapsing under gravity to form new stars. Imagine a cloud of gas being squeezed into shape by a network of magnetic ropes. These fields provide a counterbalance to gravitational forces, slowing down the collapse process. This delicate tension allows the gas to cool and condense more gradually, fostering the formation of a dense core that will eventually ignite into a star. Furthermore, magnetic fields contribute to the angular momentum problem in star formation. As gas and dust collapse to form a new star, they begin to spin faster, much like a figure skater pulling in arms. Without a mechanism to shed this angular momentum, the material will be flung out, preventing the formation of a stable star. Magnetic fields help redistribute this momentum by channeling some of the energy away through outflows and jets, effectively acting as a braking system. These outflows can sculpt the surrounding environment, clearing away excess material and influencing neighboring star formation sites. Thus, magnetic fields are not passive bystanders but active and dynamic participants in the complex ballet of star creation. The phenomenon of irregular and fast rotations in some stars is a fascinating chapter in the cosmic storybook, driven by various dynamic processes and stellar interactions. On one hand, these rapid spins can be a relic of their origins. Stars begin their lives within the swirling confines of molecular clouds, and the conservation of angular momentum plays a crucial role. As they collapse into denser forms, much like an ice skater pulling in their arms to spin faster, a contracting star increases its rotational speed. Variations in the initial conditions of the molecular cloud, such as turbulence, magnetic fields, and the distribution of angular momentum, can lead to stars with inherently fast, irregular rotations. On the other hand, interactions during a star's lifetime can significantly alter its spin. For instance, star systems with close companions, such as in binary or multiple stellar systems, frequently exchange angular momentum through gravitational interactions. When two stars in a binary system are close enough, tidal forces come into play, rapidly spinning up one or both stars if mass transfer occurs. Furthermore, stellar mergers and close encounters can impart angular momentum to stars, rapidly increasing their rotation rates. Even isolated stars can experience rotation changes due to magnetic activity and stellar winds. These processes can lead to the loss or redistribution of angular momentum, sometimes resulting in irregular rotational velocities. In the grand cosmic dance, the factors contributing to a star's rotation are a blend of inherited traits and dynamic experiences.